Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about how to estimate the probability density function of a continuous random variable without assuming a parametric model. We will see that there are two main techniques, the histogram and kernel density estimation, and they're very related. Let's get to it. We're going to talk about the histogram and kernel density estimation. The ultimate goal is to estimate probability density from data. Let's remind ourselves what the probability density means. A probability density tells you what is the probability that a random variable is in any part of the real line divided by the length of an interval close to that point. So here we're interested in the point A. The probability density at A tells you the probability that this random variable is here in an interval very close to A divided by the width of the interval. So how do we estimate probabilities from the density? We just integrate the density or whatever region we're interested in. Okay, the thing to remember is that probability density is probability divided by the length of an interval when the length becomes really, really small. There's a whole video on probability density. If that wasn't clear, you can go take a look. The actual formal definition of probability density function of a random variable is that it's the derivative of its CDF. So now you could say, well, in this other video, I saw that you can actually estimate the CDF from data. It's called the empirical CDF, super easy to do. Why don't we just do that and then take the derivative? Well, we need to take a look at that and see why that's not going to work out. Remember that the empirical CDF is obtained by computing the empirical probability that the random variable is smaller or equal to any value on the real line. Remember that this is an indicator function that just counts how many data points are smaller or equal to A. Okay, we sum them and we divide by the total number of points. The thing is that when you actually look at an empirical cumulative distribution function, an empirical CDF, it looks like a staircase. Why? Because this is where these little lines are the points. In between the data points, this thing is just constant because the empirical CDF is the probability, is basically the fraction of points that are to the left of each value in the real line. So it only changes, like here, for example, there are these many points. This is why the CDF is equal to that. It's just constant in between, right, until we see another data point. So weirdly enough, and I already mentioned this in the video on the CDF, the empirical CDF of a continuous quantity is not a valid CDF of a continuous random variable, okay, because it only assigns probability to where we see data. So that is not going to work out. What can we do? Well, let's think about what we need from a PDF. A valid PDF needs to be non-negative and integrate to 1. If we manage to get a PDF that satisfies those two conditions, it's going to be a valid PDF. As we explained in the video on the mathematical definition of continuous random variables, we could reverse engineer a probability space from it, but that's not too important because we're never going to do that. But it's mathematically legitimate if you want. So how do we estimate this thing? We cannot use empirical probabilities because the probability of each data point of a continuous random variable being equal to each specific value is always going to be 0. So that's not going to work out. We cannot use empirical probabilities directly. We will use them in some sense. So instead, we need to make some assumptions about the density. We're going to have to make some assumptions about the density in order to be able to estimate it. What we're going to assume is that it's constant, and later on smooth, but for now constant, in certain intervals. That's the assumption we're going to make. Okay, if we do that, if we assume that the PDF is constant in certain intervals, then we get the histogram. Okay, this is the first technique that we're going to look at, which gives us an estimate of the probability density. So the logic is the following. We say, okay, since the probability of being in an interval is equal to the density times the length of the interval, if we assume that the density is constant with the interval, we just need to compute the empirical probability and divide it by the length of the interval. And that's exactly what we do when we compute a histogram. We divide the real line into bins. we compute the empirical probability of belonging to each of the bins, and then we normalize dividing by the width of the bins so that we get a valid PDF. Let me draw a very simple example. So we have the real line, and let's say that we decide on, you have to decide where the bins are. Let's say that we divide the real line into these bins. And now we see these data points. 2 data points in here and 1 data point in here. So what do? We say, okay, the empirical probability of belonging to this bin is 2/3, right? Now this is going to have a certain width. The bin is going to have a certain width. So we're going to basically have a density estimate that is constant with that bin, that is going to be 2/3 divided by the width of the bin, which is here, I'm going to call it W. Here, there's 1/3 of bin in here, so the density is going to be 1/3 divided by W. Why am I dividing by W? Because I have to divide by the length of the interval in order to get a density, so that this whole thing integrates to 1 and we get a valid PDF. Okay, and that's it. That's a normalized histogram to estimate probability density. It's actually very simple. And this is what we get if we compute a normalized histogram for the height in the US Army. Actually, this is the histogram just with the counts. So here we're just counting how many soldiers, in this case, end up in each bin. And now we have to normalize so that everything integrates to 1 and we have a valid PDF. So this is a valid PDF because if you compute the area under it, it's going to integrate to 1. And this gives us an estimate of the probability density, in this case of height in this population of people. Let's define this a little bit more precisely. If we have data that we know are going to be in an interval of length L, then we divide L into B bins of length L over B. I was saying width before. I never know if I should say width or length. Let's go with length since it's written on the slide now. So this would be the W before, which was, it's kind of annoying, right? That I used width and then now length. Hopefully that's clear. Okay, so we do that. We divide to these intervals of length W. Now we count how many points land in each bin. Again, there's an indicator function that is equal to 1 if the point is in that bin and 0 otherwise. We sum over all the points. That's how we get the actual histogram without normalizing. But now we have to normalize dividing by the number of points so that this becomes a probability. And then we also have to divide by the width of the bin so that it becomes a density. Okay, so that's why we're dividing by N, and also we're dividing by this W that was the width or the length of the bin. Sorry for using width and length interchangeably. All right, so at the end of the day, we can interpret this, if you want us, every time we see a data point, we are adding a rectangle. Actually, this is probably easier to see in my original picture. So let me go to my original picture. So in this original picture, if you think about it, what are we doing? For each data point, we're kind of adding a rectangle to the density. And that rectangle, the height is 1 over n divided by the width. And the width is whatever it is W. Again, I'm using width instead of length. I guess I just like width more. I should just accept it and move on. So this is how we're building the histogram. We're adding these rectangles. Okay. And that's how we get the histogram. This is what I'm calling this pi of JT. This is the rectangle corresponding to the point xj. Okay, so when we have a point xj in a bin, we add a rectangle there to the density. The height of that rectangle is equal to 1 over n, so that this is a probability, and 1 over the width, which is L over B. So this becomes B over NL, so that it becomes a density. Okay, so this is completely equivalent to the description I gave you before. And now we have to think, is this a valid PDF? Well, for it to be a valid PDF, it has to be non-negative. It's clearly non-negative, right? It only has non-negative values because everything we have discussed, there's no negative numbers here. It also needs to integrate to 1. We're just considering rectangles, so we can just sum the area of all those rectangles. How many rectangles do we have? Well, we have n rectangles, and the area of each of them is their width or length, L over B, multiplied by their height, which is B over NL. That area is going to be 1 over n. We have n of them. When we add all those areas, we have a histogram that adds up to 1. So essentially, I'm saying a little bit more formally what I was saying before, that if we normalize appropriately, we're going to get a valid density that is going to integrate to 1. Again, this is what happens for our data set for the US Army if we use 50 bins, 20 bins, and 10 bins. So realize that when we use less bins, what happens is that we get some noise. And there's the eternal question, right? Is this noise or is this actual structure in the data? Here I would be willing to bet that this is noise. There's no reason why this is smaller than this and this. Okay, I don't think that's actual structure in the data. In order to check whether it's actual structure in the data, you would have to have some held out data. So the number of bins is actually a very important hyperparameter. If there are many bins, you're going to get more noise, but a more detailed description of the density. If you increase the bins, your empirical probabilities are going to be better. So you're going to have less noise, but you're also going to have less granularity. Here we have very few bins, and now we don't really know as well what is going on with the density within the bins. Okay, so there's this trade-off. Usually if you have a lot of data, you want to make your bins narrower. You want to have more bins because you can afford to get more granularity, more granular information about your density. This is another histogram of GDP per capita. The previous one was height in a population of soldiers. This is the GDP per capita for many countries. If you remember our video on the CDF, there we showed that the CDF indicated that there were very few countries that were very rich, and then there was some kind of tail of rich countries, and then the vast majority of them were very poor. This is very obvious when we look at the histogram. This is what happens if we use more bins. There's a bit less noise. So here again, it seems very plausible that this is just noise from the fact that we don't have that many data points to compute these empirical probabilities. There's no reason, it doesn't seem very intuitive that this should be higher than this. If you decrease the number of bins, you have less noise, but eventually you also have much less granularity, okay, in your estimates. Okay, so now let's think about how we defined this in terms of these rectangles that we were summing. And then maybe I'll draw a picture to remind you. So we were dividing the real line into bins. And we were saying, well, here we have 2 points, here we have 1 point. What we're saying, okay, now to build the histogram, we're adding a rectangle per point. Okay. But now imagine that you have a point, that a data point ends up being here. That rectangle corresponding to that data point is centered at the center of the bin. And that's kind of not very satisfying, right? Because the contribution of this data point to the estimate of the density is actually only, so the contribution only goes from here to here. There's no contribution here, even though that part is closer to the data point than this part. So this is kind of rigid. How about we center those rectangles at the actual data points? That makes more sense, it seems to me. And in fact, that's what kernel density estimation does. This is kernel density estimation with a rectangular kernel. For some reason, in data science and machine learning, we like to use kernel for many things. In this case, kernel just means the function that you're kind of summing up to build the density. Okay? I don't know why we like this word so much. So now we have these 3 data points. What we do is, boom, we put a this rectangle that has a certain width, which is a hyperparameter at x, we have to make sure that the height is determined so that at the end of the day everything integrates to 1, like in the histogram. Now we put another rectangle at this second data point. The crucial difference with the histogram is that these guys are centered at the data points. Otherwise, they would be centered at the center of the bins. And another one for the third point, and boom, this is our estimate of the density, which is more flexible. It adapts to the data structure in a bit more flexibly. I hope flexibly exists as a word than the histogram. Do we need to use rectangles? Why is it not very satisfying to use rectangles? Maybe think about it for a moment. The reason it's not very satisfying is that the contribution of this guy to the density is the same in points that are kind of relatively far away to it as in points that are kind of close. It would be maybe more natural for it to contribute more close to where it is and less as you go away. Okay, and that is like kernel density estimation can account for this, replacing the rectangles by a smooth function that peaks at the center, at the data point. Okay, if you do that, for example, with a Gaussian kernel, that is a very common choice, this is what you get for our example. You get a much smoother estimate of the PDF that just seems more natural. Okay, so at the end of the day, how do we build a kernel density estimate? We choose a certain bandwidth. Don't worry too much about the bandwidth, but just very quickly, the bandwidth tells you how wide this kernel is. So in the case of the rectangles, it's directly it determines directly how wide the rectangle is going to be. In the case of the Gaussian, how stretched out it is or not. Okay, you choose that. This is a hyperparameter. We'll talk in a moment about the effect it has on your probability estimate, your density estimate. And then as long as the kernel is non-negative and it integrates to 1, then you're going to get a valid PDF. Because realize that here, this H and H just ensures that the kernel still integrates to 1. So when we add all of these areas, we're going to get n times the area of the kernel, but we're dividing by n. So the whole construction is going to integrate to 1. So as long as the kernels are non-negative, it's also going to be a non-negative probability density estimate. You're going to get a valid probability density function in this way. Again, the only difference with the histogram is we're not centering each of the contributions to the density at the center of the bins. We're centering at the data points, and we can choose not to use a rectangular function to build the density. We can use more smooth functions such as the Gaussian. Okay, as a summary, maybe the estimate is composed of copies of the kernel that are centered at each of the data points. Is the estimate a valid PDF? I already gave this away. It is because each of these copies integrate to 1. We have n of them, and we're also dividing by n here, so they're going to integrate to 1. Okay, so what happens if you pick kernels that are very thin? Similar as in the case of the histogram, you're going to get a noisy estimate where you're going to get some structure that is probably not really there. It's just noise from the fact that we don't have enough data points. This is the same data as before, the one about the height in the US Army. This is the same effect as when we have a lot of bins in our histogram. The bins are very narrow. How can we alleviate this? By using a wider kernel, and then we have a smoother estimate that looks much more reasonable. If we over smooth, we're going to lose some structure. So there seems to be some asymmetry here that between, around the peak that seems to actually be there. We don't observe this if we over smooth by using kernels that are too fat. This is the same example for the same example. This is the example about GDP per capita. Here we're applying again kernel density estimation. I should have said this before. This is with Gaussian kernels, this example. This also with Gaussian kernels. We see this, that is probably an artifact. This structure is probably an artifact of the fact that we don't have that many data points. We can deal with it by using a wider kernel, but we're going to lose some granularity there. And that's just a trade-off that is just going to be difficult to navigate This is a very good example because we have a situation here where probably the probability here in between should never be 0. But if we make the kernel wide enough to account for that, then we really suffer over here where we have many, many data points. This suggests that you could, in principle, use different bandwidths in parts where you have high density than where you have very low density. And there exist variations of kernel density estimation where you can actually do that. Or you could just transform your data points by a known transformation so that they're not as imbalanced. It depends what you want to do with your probability density estimate. Okay, so what have we learned? We have learned how to estimate probability densities from data without assuming a parametric model. In the next videos, we will see what we do if we want to assume a parametric model. These are non-parametric estimators, if you want to get fancy, of the probability density of a continuous random variable. They're the histogram and the kernel density estimate, and as you saw, they are very, very connected. And that's all I got. Thank you very much.